So today starts the second module of your term. And the first topic for this module is strain. So as usual, let's have a bit of an introduction. First, let's define what's strain. So strain is simply the geometric quantity that measures the deformation of a body. So previously, on your Mech 30, statics of rigid bodies, you just talked about forces, the types of forces involved, and types of systems. And then in the start of our strength of materials, we talked about stress. Okay, and then another effect of force, aside from stress, is strain. So again, strain is the deformation of a body. We have two basic types of strain, your normal strain and shear strain. Normal strain is dimensional changes. Shear strain is distortion, which is change in angles. So it's a bit similar to your types of stress, normal stress, shear stress. Normal stress being stress uh, caused by the force perpendicular to the cross-sectional area. So it's kind of similar here for normal strain, wherein it's a dimensional change. So instead of perpendicular parallel areas, we're just talking about change in length, change in area, change in thickness, etc. No matter depending on how your object deforms. So we'll focus on normal strain first. So normal strain, also known as axial strain, is the elongation per unit length. Now, although this is length, it's not always confined to just the dimension of length. Okay, again, it could lead to area, diameter, etc. So you have two types, your uniform deformation and non-uniform deformation. For uniform deformation, we'll be solving for average axial strain. And the equation is epsilon equals delta over L, epsilon being your strain. Delta is the axial elongation and L is the original length of the member. For example, looking at the figure on the right, this is your rod, okay? And then it's acted upon by an applied force P. Because of this P, your rod elongated by this amount, which is your delta, the amount your object deformed. And then L sub O, or L, is simply the original length of your member. So that's for uniform deformation. If we have non-uniform deformation, what we solve for is strain at a point. Because for this, okay, strain experienced by your object is different along the parts of the object itself. That's why instead of average, we're looking for strain at a specific point. And because of that, we're going to employ integral calculus in solving for that strain. So strain is the limit of your change in deformation over change in length as your change in length approaches 0. And we can rewrite that if we're talking about differential lengths as your differential elongation or differential deformation over differential length x. Okay, and then integrating this equation from 0 to total length L, we have strain equals deformation times the integral of strain times differential length x from 0 to total length L. Now for our class, we'll be focusing more on uniform deformation. Okay? So similar to your stress, this also has sign convention. So you have positive strain if it's in tension, and then negative strain if it's in compression. So same thing with your stress. So if your object is stretching or elongating, that's positive strain. If your object is compressing, that's negative strain. So keep that in mind when we solve for problems involving strain. Next, we have your stress-strain diagram. So to create a stress-strain diagram, we do a tension test. So under that, a sample is subjected to a controlled tension until failure. Continuous readings are taken of the applied load and elongation of the gauge length. The data are then converted to stress and strain. So for example, you have this rod, a sample. Gauge length is the original length taken from the sample. And then a continuous load is applied to that. Because of that load, it's going to stretch or elongate. And then you're going to compute or measure out that load and elongation. And then from those two, you can compute stress and strain. So plotting the actual stress versus actual strain results in a stress-strain diagram, which looks something like this. So let's talk about this. Okay, as you can see, strain on the x-axis, stress on the y-axis. So looking at this triangle, we call this region your first stage, which is the linear elastic region. In this region, the stress is proportional to the strain. Hence, we have a straight line. And that means it obeys the general Hooke's law. We'll talk more about that later. And the slope of this line is your Young's modulus. So in this region, the material undergoes only elastic deformation. That means after your object deforms, it's gonna go back to its original shape. Now, going further from 0, you'll see that you'll hit this proportional limit. So the proportional limit is the point on a stress-strain curve where the linear elastic deformation region transitions into a non-linear plastic deformation region. So it starts transitioning from elastic to plastic. Okay. So in other words, the proportional limit determines the greatest stress that is directly proportional to strain. So anything above that, stress is not proportional to strain anymore. Hence, that's why we call that proportional limit. So after your proportional limit, you also see this point, close to that, your elastic limit. Elastic limit is the point at which there is no permanent deformation in a structure, or the point at which the body regains its original shape. Now, its difference from proportional limit is simply the point at which stress is still directly proportional to strain. So proportional limit just talks about relationship between stress and strain. Elastic limit talks about the deformation of your material itself. Once again, for the elastic limit, this is the point where your object starts deforming permanently. And then the end of this stage is your yield point. So it ends here. Okay? And then the yield point is the initiation point of plastic deformation. And the strength component of this yield point is simply your yield strength. Now recall, we talked about yield strength before, right? We considered that the maximum stress your object can withstand. Now we don't design according to this yield point, right? We want to use a working stress. So that's because yield point, again, although it's the maximum, we want to design conservatively. Okay. Also mentioned before that yield point or yield strength is the strength beyond which your object starts deforming permanently. So you want to work in the elastic region so that your material still goes back to its original shape. Okay. Now beyond that, we go into the second stage, which is the strain hardening region. So this region starts as the stress goes beyond the yield point, and it reaches a maximum at the ultimate strength point here at the top. And this is the maximum stress that can be sustained, and we also call this the ultimate tensile strength, or UTS. Okay. Now, ultimate strength is the maximum stress that a material can withstand before it breaks or weakens. So here, the point where your object will still go back to its original shape, or point where your object starts deforming permanently. And at this point, your object starts breaking or weakening. Okay, so here it just deforms. Here it now actually breaks. And then after that, we move on to the third stage. Okay, and the third stage is what we call your necking region. So beyond tensile strength, a neck forms where the local cross-sectional area becomes significantly smaller than the average. So to give you a visualization, let's say this, right? Let's just ignore this as a sample. Let's say this is a rod of uniform length or uniform cross-sectional area. Okay, necking occurs when the cross-section of this suddenly becomes significantly smaller. So something like this. Hence a neck, right? Something that suddenly thins out. That's why it's called the necking region. Okay, and then at that point, this region eventually ends up with fracture. Okay, so it fractures at these points. So later I'll discuss the difference. So at this point, the engineering stress decreases. And as you can see, the curve starts sloping downward. Now, the reason for this is because the force lessens. Okay. So remember that for this test, we want to maintain a constant strain rate all throughout. Okay. And since after necking, it's going to be easier to maintain that strain because the area is smaller. Hence, the force needed to maintain strain also decreases. Decrease in force means there's a decrease in stress. That's why it's going to slope downward. Now note that although the pulling force is decreasing here, the true stress keeps growing because the shrinking section area is not actually considered. So to give you a visualization, let's have this. Right? So this is your normal rod or specimen, right? With a normal cross-sectional area over here. Okay? Okay? So the basic cross section over here, let's call this stress 1 equals F over A. Okay, original force, original area. Okay, and then when necking happens, this is how that looks like, right? So when necking occurs, so this is the original area. But here, when necking happens, this is what happens. So this portion suddenly shrinks. That's why we call it necking. And now this is the area in consideration, the critical area. Okay? And then let's call that stress 2, F over A2. Okay? So that's the necked area. And obviously that A2 is much less than your original area. Therefore, you can say that the stress here, and we call that the actual stress or true stress or actual rupture, right? And then this stress is greater than this stress because area is smaller. Remember, stress and area are inversely proportional. The smaller the area, the greater the stress. Okay, so this is what actually happens. Your stress should increase. And that is illustrated by this curve right here. This is what happens when you consider area, decrease in area. That's your actual rupture strength. And this is what happens when you don't consider area because there's a decrease in force. Okay, so we call those points actual rupture strength and rupture strength. So once again, rupture strength is based on original area and original gauge length. Actual rupture strength is based on the actual decreased area and increased gauge strength. And rupture stress or stress is stress at which failure occurs. So at these points, your object has failed already. So here it starts fracturing, breaking. Here it essentially or ultimately fails. And then ultimate stress is the high stress in the stress strain curve. Okay, so those are the basics of your stress strain diagram. Now let's go further into those individual points. Let's start with your proportional limit and Hooke's law. So Hooke's law is just the manifestation of the straight line from your origin O to a point called the proportional limit. So from here to here, right? As mentioned earlier. Hence, Hooke's law is no longer valid beyond the proportional limit. So we only use this along that first region. So according to this, for relatively small deformations of an object, the size of the deformation is directly proportional to the load. So by definition, let's create an equation. All right. According to Hooke's law, okay, Deformation directly proportional to your load. Okay. So deformation directly proportional to load, and that load creates your strain. Sorry, deformation rather. Deformation directly proportional to your load. It's your load P. And this deformation relates to strain, and this load relates to stress, right? So this is strain and stress in terms of that. And then you can say that stress is directly proportional to your strain epsilon. And remember, to create an equation out of proportionality, we introduce a proportionality limit. So usually that's K, right? So we'll say KE. Now this K, it has a specific name in terms of stress and strain. And we call that your Young's modulus E. Okay? So that's the equation. Now another thing is, remember this happens along the straight line, right? So let's draw that graph again. And I've mentioned earlier, the slope of this line is your Young's modulus E. And remember, slope is rise over run, right? The rise here was your stress, the run here was your strain. So equate that, that's stress over strain. So multiplying both sides by strain, you get stress equals E times strain, which is the same thing here. Okay? So those are some ways to get that equation. So again, sigma, stress, epsilon, strain, E, Young's modulus, also known as modulus of elasticity in pascals or PSI. Now, usually the material in question is steel. You should remember that modulus of elasticity of steel is 200 GPa or 29 times 10 raised to 6 PSI because it's something we use very often. Now, after proportional limit, we have elastic limit. It's the limit beyond which the material will no longer go back to its original shape when the load is removed, or it is the maximum stress that may be developed such that there is no permanent or residual deformation when the load is entirely removed. Again, elastic limit, point where permanent deformation starts. And then next is yield point, the point at which the material will have an appreciable elongation or yielding without any increase in load. So like it's an appreciable deformation already, something we don't want to happen with our material. So that's why we consider the yield point as the maximum stress your material should withstand. So for structural steel, load may decrease while yielding occurs, which I mentioned earlier in explaining the stress strain diagram. Now again, we don't want to design according to this maximum stress or yield strength. We want to design according to a working stress. And remember, we got that working stress by the use of a factor of safety. Okay? So working stress, also known as allowable stress, denoted by sigma sub W, is the maximum safe axial stress used in design. Now recall, in one of our previous examples, we called factor of safety as Fs. And Fs is maximum strength or maximum stress over working strength or stress. Therefore, working stress is simply maximum over factor of safety. Now, there's two maximums here. One is from the yield point, one is from the ultimate point or ultimate yield. So why is it different? So the reason for it is because it depends on the material. So in most designs, the working stress should be limited to values not exceeding the proportional limit so that the stress remains in the elastic range, right? If you think about it, we shouldn't consider yield point. We should consider elastic point because after elastic, or rather after the proportional limit, your object deforms more. But again, it's hard to figure out what that point is exactly. Okay, so instead, it is customary to base the working stress on ultimate strength or yield point. Now again, the difference is because of the material used. If we're using structural steel, yield point is selected as basis because it is the stress at which a large permanent set of deformation may occur. While for other materials, working stress is based on ultimate strength. Because again, steel, especially for steel, we don't want it to deform. Because after yield point, object starts deforming. For some materials, that's fine. That's why you can work up to ultimate strength. For steel, however, we don't want that. We don't want your steel to deform. Okay? And so now let's get more specific. Let's talk about actually loaded bars. So the condition there is load must be axial. The bar must have a uniform cross-sectional area, and the stress must not exceed the proportionality limit. And the equation for this is the following. Deformation equals sigma L over E or PL over AE. Once again, let's try to get that equation. Okay. So this is actually loaded bars. Right? So recall from the first slide, right? Strain is deformation over original length, right? Now another thing to recall is this, right? Stress equals E epsilon. Now from this, you can create an equation for deformation, which is simply this, right? And then, subbing that here, epsilon is simply sigma over E, right? Sub that here, you'll see that deformation is sigma L over E, right? Where sigma is the stress due to your applied load P. Now from that, can anybody give me what's the equation for stress again? Correct, Burst and Emmanuel. Wico, Burst. Emmanuel pala. Alright. Wico, G, Burst. P over A. So I can sub that here. So or deformation is simply P over A times L over E or PL over AE. So once again, this is the equation for deformation due to applied load. So you'll use either depending on what's given. If stress is given, use this. If force is given, use this. Okay? And then again, P, actual force, L, original length of member, A, cross-sectional area of member, normal to P or perpendicular to P. Okay, keep this definition in mind. And then E is modulus of elasticity or Young's modulus. So that's for uniform cross-section. If the cross-sectional area is not uniform, the actual deformation can be determined by considering a differential length and applying integration. So instead of PL over AE, we use P differential length L or differential length X over AE. Integrate that from 0 to total length L. Where A is T, Y, T being the thickness of your element, and Y being the height of your element, hence giving the area of a rectangle. And Y and T, a variable, must be expressed in terms of X. Okay? Now let's get a bit more specific. Instead of just actually loaded bars, let's talk about suspended bars. So for a rod of unit mass rho, so unit mass also just means density. So unit mass rho suspended vertically from one end, the total elongation due to its own weight is the following equations. So again, let's derive that. So suspended rod. Right? Let's draw a rod suspended here. And okay. All right, so we're gonna solve this using integration. Now remember, it was mentioned that to use integration, you're gonna use a differential length L. So let's say here, right? I'm gonna use this. This is my differential length, and that's dx. Okay. Now this dx has this portion attached to it. Now just imagine a very thin piece of metal with negligible weight, right? If there's something attached to this metal below it, It's causing that metal to pull downward, right? And what's causing it to pull downward is the weight of this section itself, because there's no applied load here. So doing that over here, right? This portion exerts weight on your differential length, right? So this has weight, W. And that is the force causing deformation. Now let's create an equation of that weight. Okay, so again, now we know weight is simply the force, actual force acting on your element, this part. To create an equation for weight, recall that density is simply mass over volume. And then mass is just density times volume. If I multiply everything by gravity, G, right, you'll get mg equals rho gv. Mg is weight, rho gv. Therefore, your actual force is also equal to rho gv. Okay? So again, let's differentiate. This is P, this is rho, this is rho. Okay? Now that we have an equation for P, let's go back to the integral equation. Delta equals integral from 0 to L of P dx over AE. Okay? And then let's just sub our values for P. P is this, rho GV. So rho GV dx over AE. Oh, what's this V? V is the volume of this. We can create an equation for that, right? 0 to L rho G V. So consider this as a length with area, cross-sectional area rather. This, right? This is the cross-sectional area. So this is the volume. Now let's call that X. Okay? So this portion has length X. And then this total thing has length L. Okay? Yeah. So the volume of this, again, is just cross-sectional area, right? Consider this as a rectangle, times height, which is X. So AX dx over AE. Okay, as you can see, A cancels out. We'll be left with integral rho G x dx over E. Now in integration, it's easier if we can factor out constants. Constants meaning values that won't change no matter what you do to the object. So can anybody tell me what are the constants in this equation? Or just one? Constants of the equation. Correct, Eric, Ablao, Mariah, Cavero. Ablao, Cavero, who else? Cyrus, correct. Who else? One more. And then Chloe, correct. Macrohon. And then it's rho, G, and E. Density, gravity, modulus of elasticity are all the same no matter what you do to your material. So I'll factor that out. Rho, G, over E. And then integral of x dx from 0 to L. Does anyone remember what's the integral of x dx? Correct, Emmanuel. Who else? And Mariah. Cavero, verse. It's x squared over 2. So x squared over 2. And then just sub in 0 and L. So subbing L first, you'll have rho G over E times L squared over 2. And then minus 0, right? 0 squared over 2. So therefore, you can say deformation is simply rho G L squared over 2E. So that's one of the equations, okay? Now another thing is rho G. We can create another equation for rho g, right? Rho g is simply mg over v. Rho g equals mg over v. I'll sub that here. So, or deformation, okay, rho g mg L squared over 2ve. Now, from this, I can actually rewrite v, okay? Now, that's the volume of the entire thing. Let me just move things around, right? Yeah. So this becomes mg L squared over 2, and then the volume of the entire thing is simply cross-sectional area times total height L. So AL times E. And again, as you can see, L cancels out. Therefore, you'll get stress equals mgl over 2AE. And that's the other equation for deformation due to its own weight of a suspended rod. Okay, so those are the equations. Now, another thing is stiffness, denoted by K. It's the ratio of steady force acting on an elastic body to the resulting displacement. So force per displacement. All right, wait, there's a question. Is it necessary to understand how to derive the formulas? To me, yes. Because when you understand how you got the formula, you'll understand how to apply it in unusual problems. So instead of memorizing the equations, because sometimes your memorized equations don't apply to certain problems. So you can manipulate that equation if you know how it was taken. Okay. That's why I'm showing you how everything was derived, right? Because I don't want you to just memorize equations and apply it. I want you to understand the concepts behind the equations, okay? And so anyway, according to this definition, it's force per displacement. So force is P, displacement is delta. It's okay, simply P over delta, and force is in Newton, delta is in millimeters. Okay. Now a few things, few notes on the computation of deformation before we start problem solving. P must be found from equilibrium analysis. That's from free body diagrams, summation of forces, etc. We have positive P for tensile force, positive delta for elongation, negative P for compressive force, negative delta for shortening. Make sure units are consistent, and it is common practice to let the units of E determine the units to be used. So E, again, Young's modulus, usually in pascals or PSI, Newton millimeter, Newton meter, or pound per square inch. Also, sometimes, since we're used to it, we can use MPa, Newton per millimeter squared. Now, if axial stress is in the elastic range, delta of a bar is very small compared to its length. So, if you got an answer for deformation that's quite large, then that's your clue that you did something wrong. Because again, if we're in the elastic range, delta should be small. Not just small, it's very small compared to the original length. Okay? And so those are the things to remember. Right, before we move into the problem solving part, do you have any questions? Please answer in the chat. Ma'am, kailan po namin malalaman kung kailangan mag-derive? If you forgot the equation, or if your equation is not suitable to the problem at hand. Later, I'll show you a small example of why understanding concepts is important. Okay. Right. So no questions. Let's have an example. Number 1. Bring out your calculators. Okay, let me just edit this. A steel rod having a cross-sectional area of 300 millimeters squared. So I'm going to write the given as we go. So area 300 millimeters squared, and a length of 150 meter, is suspended vertically from one end. It supports a tensile load of 20 kilonewton. So that's your load, P, 20 kilonewton at the lower end. If the unit mass of steel is 7850, again, that's density, 7850 kilogram per meter cube. E is 200 times 10 raised to 3 meganewton per meter squared. And that's the same as MPa, 200 times 10 raised to 3 MPa, Newton millimeter. Find the total elongation of the rod. So let's try drawing that first, right? We have your rod suspended vertically, and then we have the applied load, supports tensile load at the lower end. Let's have that. Here's the lower end, it's supporting 20 kilonewton. So we have elongation due to load. Do you remember what's the equation for deformation due to load? What's the equation again? Correct, Jan. Guico and Chloe. Very good. It's PL over AE, or sigma L over E. So memorize this, or rather this. It's easier if you have this memorized because it's the basic equation for deformation due to load. P given 20 kilonewton. Now remember, we wanna follow the unit of your E. This is E, that's Newton millimeter. So I gotta convert this to Newton. So I'm gonna multiply it by 1000 or times 10 raised to 3 to convert kilonewton to Newton. And then L, length 150 meters. Again, I want that in millimeter because it's Newton millimeter. So I'm gonna multiply it by 1000 again or times 10 raised to 3. They're the same thing. Meter to Newton, meter to millimeter. And then over A, 300 already in millimeters, so that's great. And then E, 200 times 10 raised to 3. From this, please solve what's delta. Correct, Christian? Ganaga. Who else? Correct, Elgin. Meneses. The answer is 50. So 50 millimeters. All right, are we done? This is the answer. Please answer in the chat, yes or no. Is that our final answer? Okay, correct, it's not. Can anybody tell me why isn't it the final answer yet? Okay, correct, Cyrus. Okay. Cyrus pa lang nakakakuha. Anyone else? And a specific reason why is it not done? What's missing? It's correct, total elongation, but why isn't this a total elongation yet? Correct. Yeah, correct, Gabriel, Marinay, and Emmanuel. Rico, Marinay. Very good. Because, again, we have a suspended object. When we have a suspended object, we have elongation due to weight. Okay, very good. We have an equation for that, right? Elongation due to weight is simply rho GL squared over 2E. Rho GL squared over 2E. So I'm going to specify this. Due to load, I'll call this rho P. Due to weight, I'll call this rho W. Okay, now let's just sub in our values. Let's start with the rho, which is 7850. Okay, 7850. And then G. So one thing about this 7850 is kilogram per meter cube. Remember, I want Newton and millimeter. Okay, so I'm gonna convert meter cube to millimeter. So that's kilogram meter cube. And then this is conversion. 1 meter is 1000 millimeters. This is cube. So I gotta cube this as well. Okay, so conversion. Okay, so that's density. Next, gravity, 9.81 meter per second. Now, this is meter per second. I'm not gonna convert that. Now you might be wondering, oh, why aren't you converting that? Because what we'll have here is kilogram meter per second, which is Newton. And that's what I want. Newton, right? Newton millimeter. That's why I'm not converting this. Okay? Because this creates kilogram meter per second, which is Newton. Right? Next, L squared. L is 150. Again, that's meter. I'm gonna convert that to millimeter by multiplying by 1000, and then that's squared. Okay? Next, 2E. And then E is as is. 200 times 10 raised to 3. Okay, from this, please solve what's elongation. Correct. Christian and Gabriel. Danaga Narimay. It's 4.33 millimeter. Okay, so again, this isn't the final answer. Final answer, total elongation is the sum of your elongation due to applied load and weight, and both of them are creating elongation or stretching. That's why they're both just positive, just a sum. And final answer is 54.33 millimeters. And that's it for number 1. Do you have any questions for number 1? Please answer in the chat. If none, let's have number 2. Number 2. A steel wire 30 feet long. I'll write that. L, 30 feet. Hanging vertically supports a load of 500 pounds. So that's your applied load, 500 pounds. And again, it's vertical. Hanging vertically. Neglecting the weight of the wire, determine the required diameter if the stress is not to exceed 20 ksi. So that's your working stress, 20 ksi. Total elongation not to exceed 0.20 inches. So deformation limited to 0.20 inches. And then E is 29 times 10 raised to 6 psi. All right. So we're looking for minimum diameter. And then we're given the following. Now recall in our previous lectures, I've mentioned the amount of stress given is the amount of equations you need to create and the amount of answers that are possible. Now we have an additional condition, which is your elongation, your strain. So now the amount of stress and the amount of deformation given is the amount of equations you need to create. We have one for stress. We have one for strain. So let's do each. Let's start with stress. We already know stress is simply force over area. Okay? Now, stress is limited to 20 KSI. Remember, we usually follow the unit of our E, PSI. 1 KSI is just 1,000 PSI. So I'll do that, 20 times 1,000 or times 10 raised to 3. To convert KSI to PSI equals P over A. Now what's that P? Now answer in the chat, yes or no. Is this P just 500 pounds or should I consider the weight of this? Only 500 pounds, yes or no? Okay, very good. Everyone got it correct. Yes, it's only 500 because it was mentioned here, neglect weight of wire. You can just ignore the weight. So it's just 500. Okay, very good. And then A. This is a wire. What's the cross-sectional area of a wire? What's the equation? Anyone? Equation for a cross-section of a wire. Correct. Gabriel and Chloe. It's a circle, right? Cross-section of a wire is a circle, so that's pi over 4 d squared. And then from this, you can solve for d. What's the answer? For those who don't have recitation points yet, what's the answer? Correct, Stephen. Who else? And Marino. Squared pa yan. It's still squared, so get the square root. So it's 0.18. Yeah. Inches. So that's not our answer yet. That's a possible answer. So just keep that in mind. Now we've used this. Next step is to use this. Once again, this is deformation due to applied load. So the equation that we'll use is PL over AE. Okay? And then that's 0.20. P is 500. L is 30 feet. My units are pounds per square inch. So I gotta convert that to inches, which is easy. Just multiply by 12. Over 8, we already know, it's this. Pi over 4d squared. And then E given 29 times 10 raised to 6. From this, please solve what's D. Correct, Ralph? Who else? And Benedict. Manil. Bensil. It's 0.20. Okay, again, that's not the final answer yet. That's the potential answer. So from these two, which should be our final answer? Everyone, please answer 0.18 or 0.20. Okay, almost everyone got it correct. Very good. The answer is 0.20. Again, remember, when we're looking for dimensions, we should always choose the higher value because, just taking this into consideration, this is the minimum diameter needed to limit your elongation to 0.20. Any less than that, your elongation will exceed this. Right? So you can't have any number lower than this. Hence, that's our final answer. Okay? Yeah. And that's it for number 2. Do you have any questions for number 2? Please answer in the chat. All right, no questions. Great. Let's have number 3, which is a bit more complicated. A steel wire 10 millimeters thick, 80 millimeters wide, and 1,500 millimeters inside diameter. All right, let's write all of that. 10 millimeters thick, so W 80 millimeters wide, and then 1,500 inside diameter. So I'll call that D sub I for inside diameter. 1,500 millimeter and is heated and shrunk onto a steel wheel, 1,500.5 millimeters in diameter. So I'll call that DW for wheel, 1,500.5 millimeters. If the coefficient of static friction is 0.30, so that's mu sub S, what torque is required to twist the tire relative to the wheel? Neglect the deformation of the wheel and use E equals 200 GPa. Okay. All right, before I solve, let's try drawing what's going on. Okay. So we have this wheel, right? And okay. Let's say here, that's your tire wheel. And what we want to get is the torque required to rotate this tire over the wheel. Let's call that T. Okay. Now, usually, so this is basically looking for force, right? Here it's torque as the force. Usually in solving for force, we use the given stresses and then work from that. Stress is not given here, right? So we can't use that approach. Instead, let's analyze what's happening. So you have a tire with this. It was heated, so it's gonna elongate, and then it's gonna fit over this wheel, which has a greater diameter. So because of that, when your tire cools down, it's gonna press onto the wheel, right? Your wire will press this way. In short, it creates pressure on the wheel. And now you have a tire and a wheel in contact with each other. Now, I have a question for you guys. What kind of forces are present when two objects are in contact? So recall your Mech 30, your statics. So don't think about it too complicatedly. Just have a simple understanding. For example, you have your box and a surface. What kind of forces are present here? Correct, Jan and Cyrus of Vico Tenorio. Vico Tenorio. Also correct. Meneses. Okay, wait. Okay, so one of them is friction, so you can't answer friction anymore. Okay, Meneses, correct. Let me just give points. Beltran, also correct. So there's friction. And let's say if you have an applied force here, P, there's gonna be a friction force along the surface, that's F. Aside from that, what else is present? Correct, Emmanuel. Who else? What do you think? Two objects in contact. What kind of force is there? Anyone? Okay, my friction na. What else? Aside from friction. What's the partner of friction? Correct, Joffrey. Cofreros. It's normal force, right? Normal. So if your surface is not frictionless, there will always be a normal and frictional force between two objects in contact. So same thing here, your tire and your wheel will experience a friction and normal force as well. So let's say this is your torque, right? Rotating this way, friction always opposes force. Therefore, the friction will be this way. Now let's just consider a point. Let's say this point over here. Friction, therefore, is tangential, right, to the surface it's gonna be this way, and that's your F. And then your normal force is always towards the object, perpendicular to the surface. Again, this is the surface. Perpendicular to that is this, and that's your normal force. Okay? Now, torque. Let's talk about torque. What's the basic equation for torque? From your physics class, equation for torque. Correct. Cyrus and Matthew, Briones, Tenorio, and also Nicole Beltran. Tenorio, Briones. Here. And then Tenorio. Alright, it's RF sine theta. Okay, torque. Yes. Very good. Now, if your force and your moment arm are perpendicular, that theta is 90. So RF sine 90. Sine 90 is 1. So that's just RF. Now, what's this F? Usually, what happens is, let's say you have this object, right? It's rotating about this axis. And then you have an applied force F here. This F creates a rotational motion of this object, and that's your torque. And torque here is R times F, R being the moment arm, perpendicular distance to F from the axis of rotation. Now let's relate that to what's happening right now. Okay, we don't have F. What we do have is torque. And since we don't have applied force F, what we need is to figure out what force needs to be overcome so that your tire will rotate. And as mentioned earlier, the force resisting this torque is simply your frictional force. So this is what we need, or we need a force equivalent to this so that your tire will rotate. Okay? So, in short, that's R times friction force F. Once again, I need a force equal to your frictional force so that your tire can rotate. Okay, and then R, axis of rotation to your applied force. Of course, this tire will rotate about its central axis over here. Okay? And this is your R, which is the radius of your wheel. So RW. Okay, now that's our premise. I have to get F to get R. And remember, from physics as well, F has this equation mu n. So I just have to get N. Now to get N, that's the force pressing onto the wheel. If you try to get a cross section on your tire, you can see a better view of what's happening. Right? Let's draw a circle again. Okay. Okay. And then like that. Okay. All right. There. Okay. So this is the cross section. All right. Then this here to here. Okay. And then you can do this. This is the projected area. And, okay. And then this is the cut portion on the wheel. Okay. Now, doesn't this look familiar? It looks familiar with your thin-walled pressure vessel. And we know wherever you cut, there's going to be an internal load that will appear. We cut along here for your tire, hence there's going to be an internal load that will pop out. Always, wherever you cut, there's a force. And we already know we call that force tensile resisting load, T. Okay? So that's not torque, okay? That's tensile resisting load. It's different from this. So I'll just call that T for the tire. Tensile resisting force for the tire. Okay? Differentiate it here. And then this tire experiences pressure along the sides. And that pressure can be or can create your bursting force, F. And so over here, F. Now, before we move on to equilibrium equations, we need to know what is this T. So once again, analyzing what's happening here. We have a tire, initially 1,500, it was stretched out. So it underwent deformation. We have an equation for deformation. That's PL over AE, right? Now, the deformation for this tire is not in terms of its length. It's in terms of its perimeter or just its diameter. So instead of this, that's change in diameter. Okay, so that's change in B equals P. Now this P, right, is the load causing deformation or resulting from deformation. In our case, there's no applied load. So what we'll talk about is the internal load causing deformation. Okay, or rather internal load due to deformation. And as you can see, the internal load in terms of our tire is this P. Okay, so P sub P. And then we're not talking about original length, we're talking about diameter. So instead of L, that's original diameter. And then over AE. And then let's just sub our values. Change in diameter, after expanding, it shrunk to fit this size. So that's the final. So 1,500.5 minus initial 1,500 equals your internal tensile resisting load times internal diameter, original diameter over A. Now remember from the equation, this A is the cross-sectional area normal to your force or perpendicular to your force. This is the force. Okay, this is the force, this is the cross-section of your tire. Let's specify this is a tire. Can anybody give me what's the equation for the cross-sectional area of this here? A. What's A? What's the equation of A? And let's just finish the drawing. Tire, thickness 10, so this is that 10, 10. With 80, so this is 80. Okay, and then inner diameter 1,500. Okay, now what's the cross-sectional area? What's A? Correct, Chloe. And Nicole. Very good. Beltran. Yes. It's a rectangle, right? This is the cross-section we're talking about. It's a cross-section perpendicular to your force. And that's just a rectangle, so base times height, 80 times 10. And then E is given 200 times 10 raised to 200 GPA. That's GPA. Our unit is MPA, supposedly, because we're in millimeters. So take note of this. To convert GPA to MPA, that's just times 10 raised to 3. Okay. So 1 GPA is 1,000 MPA. So I'll times 10 raised to 3 this. All right, from this, we solve what's P. Correct, Gwyneth and Benedict Faunil de Guzman. Very good. It's 53,333.33. All right, I have P now. I can use equilibrium equation here. Summation of forces equals 0, F to the right. Oh, this is Newton, by the way, because MPA. So F to the right, positive, minus, there's 2T over here. So minus twice T sub P equals 0, therefore F equals twice T sub P. Now recall this F is due to pressure, right? and then pressure over this projected area. So we can rewrite F as PA, because again, pressure equals force over area. Force is PA. Remember your thin-walled pressure vessels. So PA, A is the projected area, right? So that's 80 times 1,500 equals 2 times this. So from this, please solve what's pressure. Correct, Stephen? Who else? Correct, Christian Donald. There. It's 0.89. Correct. Okay. Now, what's the purpose of getting this pressure? Okay, remember, normal force is the perpendicular force going towards your wheel, right? And that force is due to the pressure exerted by the tire on your wheel, okay? So pressure can also be written as your normal force over area in contact or contact area, right? Because again, by definition, normal force happens when there's two objects in contact. So the pressure applied is equal to your normal force times contact area. So from this, N equals PA, right? And then you can solve for that. P is 0.89. Unit of this, by the way, is MPa, because this is all in Newton and millimeters. So MPa. So just sub that here, P. Now the question is, A, what's this contact area? Right? Contact area between your tire and the wheel. So please try to imagine how that looks like. So let me draw a 3D of the wheel, right? A very rough sketch. And let's say that, okay, this is your wheel, right? This is the cross-sectional area. I don't know, this is the surface of the wheel, okay? Actually, let's make a better one. And, okay. Yeah. This is your wheel, and then there's a tire fitting snugly over it, right? So the area in contact is the surface area of the wheel. This one, right? So can anybody tell me what's the equation for that surface area? Again, this is the wheel. Okay, while you think, I'll create a better drawing. Again, the question is, what's the equation for surface area of that wheel? No one? Surface area of a wheel? Or in short, surface area of a cylinder? No. Okay, good. This is it. This is your wheel. This is what I want. And okay. Let's see. Let me check who got it right. Ito. This is the contact area. So who got it right? Craig Burst and Gwyneth de Guzman, Manuel. Very good. Sure. Right, it's simply perimeter times thickness, right? Perimeter of a circle, that's pi d. So pi d, now this is the wheel, okay? So diameter of a wheel, that's 1,500.5. And thickness, which is W, and that is 80. Okay? What's the answer here? What's 0.89 times this, times this, times this? Correct, Eric, Blau, and Christian Dinaga. Very good. So that's 335,214.92, and then the unit here is Newton. Okay, now I have N. I can figure out what T is, right? T is RF, F is mu N. So R mu N. So T, R mu N. R is simply diameter of your wheel divided by 2. So 1,500.5 over 2 times mu, 0.30. And then this is your normal force. Right, we solve. What's the final answer? Correct, Christian. And Mariah Cavero Denado. Cavero. Denado. All right. 754, 544, 800, 8497, 75,448,497.55. And then the unit of this, okay, since our force is in Newton, so Newton times distance, which is in millimeters. So Newton millimeter. Oh, that's a very large number. So you can reduce that. Convert Newton to kilonewton by dividing by 1,000. And then convert millimeter to meter by dividing by 1,000 again. Okay, so you're dividing by 10 raised to 6, essentially. So when you do that, what you'll get is 75.45. Again, we converted to kilonewton and then meter. That's your answer. Okay, so there. That's it for number 3. Any questions for number 3? Please answer in the chat. None? Okay, great. So this is an example of why understanding concepts and not just memorizing equations come in handy. Because as you can see, the solution is not straightforward. I had to go through what is torque, right? What's normal force, what's friction, and etc. So this is why I don't want you to just memorize. I want you to actually understand what these equations mean. Okay? All right, since you don't have any questions, I'll end the lecture there. So before I dismiss you, for those who got an IP, I'll be creating an IP exam within the week. So you just have to answer that. You can watch the details of how to pass in the orientation video. Okay. So again, within the week, I'll try to upload that exam. Do you have any questions, clarifications, concerns? How about the others? Please answer as well. Yes, for those who got an I or IP, it's the same thing. Answer the exam. For those who weren't able to pass a requirement, okay, you didn't answer a seat work, an exam, a homework, whatever, diagnostic, I have to pass me an excuse letter. Okay, again, this is only for those who are not able to answer a requirement. Send me an excuse letter. Yun. But if you failed, you have to take the IP exam, even if your grade is I or IP. Okay? And any other questions, concerns? All right. Since you don't have any more questions, I'll see you on Thursday. You may go. Goodbye, class.
Thank you po, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Ma'am.
Thank you po.
You're welcome.
Thank you, ma'am.